Hey everyone, this is Yijun Qiu, and today I'm going to talk about my final project on EE591 on simulation study of low-field real-time fetal MRI. The personal goals for this project are, first of all, for me to understand more about dynamic fetal imaging. Secondly, I would like to broaden my knowledge on MRI sequences by learning the difference between SSFP sequence and the SSFSE sequence. The first goal for this project is to understand how would fetal imaging be under a lower field strength, 0.55 Tesla in this case. Secondly, I want to see if SSFSE can be applied to dynamic fetal imaging. Lastly, I would like to compare between the result under higher field strength by balanced SSFP and then the result on the lower field strength by SSFSE for fetal imaging. So my motivation for this project is that at first I did not realize that MRI can be applied during pregnancy. After I looked into that, I realized that it is needed when there exists an abnormality that cannot be defined by an ultrasound, which is the most common modality they used for pregnancy women. This is a technique that has been put into clinical usage. However, it faces few problems, such as the low SNR because of the lower volume of fetus, especially under 16 to 18 weeks. Also, there are safety concerns raised for exposing fetus in static magnetic field, and the probability of tissue healing due to the gradient. There are many solutions nowadays to solve the above-mentioned problems. For example, to use a higher field strength to compensate the SNR. However, there is always trade-off between SNR and the safety issue. In my project, I would like to also look into that. For my project, I based my work on Mr. Chris Roy's simulation of phantom dynamic fetal images under 1.5 Tesla using SSFP sequence. For my own, I implemented the SSFSE sequence, which is also called HASTE, for data acquisition. Since my goal is to study the lower field strength, I altered the T1, T2 values and made them vary with different field strength. Additionally, I added a wide Gaussian noise, which is proportional to B0, in order to generate a more realistic noise during scanning. So SSFSE, which is also called HASTE by Siemens, it is shortened for half Fourier acquisition single-shot turbo spin echo. You can see from the figure there that when compared to normal spin echo sequence, HASTE has more 180 pulse. Also, the inter-echo spacing is shorter for HASTE. In my project, I used a 1180 milliseconds for my TR and then a 65 milliseconds for my TE. For TR, it is actually way larger than the one used in SSFP, which is 4 milliseconds. Actually, for TE, it is also larger. As for the half Fourier acquisition part, I implemented an algorithm described in John Pauly's chapter called POX, which stands for Projection onto Convex Sets. It acquired 9 out of 16 of k-space data and then used the Hermitian conjugate of this data to fulfill the rest. The characteristic of this algorithm is that it uses iteration of partial k-space reconstruction to make the generated k-space data as similar to the original one as possible. In my project, it really takes 3 iterations to achieve this effect. I used data from Bottomley's paper on different tissue under different field strength. I applied the equation of T1 equals to A times V to the B, where A and B are constants for different tissues. As for T2 value, according to Bottomley, they are not dependent on NMR frequency. Therefore, I left all the T2 values constant in my project. What is needed to be noted is that the data for fetal tissues are very different from the one for adults. In fact, all the data in this paper is solely for adult tissues. I also kept all the values for fetal tissues in my project constant because of this. So, here are my results for this project. These are 3 images acquired using haste under different field strengths. The first one is under 0.55 Tesla, which is the one with lower field strength. The second one is under 1.5 Tesla, which is the field strength that commonly used in practical use for fetal MRI. The third one is under 3 Tesla. We can tell from here that the SNR is proportional to the field strength. Also, if we look into the cardiac area in these 3 images, we will see that for lower field strength, it is actually clearer in the boundaries than the ones in higher field strength, the one in 3 Tesla. In these slides, we are comparing the haste and SSFP results under the same field strength. Apparently, the SNR for haste is much more higher. It's like more than 3 times higher than the one in SSFP. And also, just by the look of it, it is noisier in the SSFP result. I think this is partially because of the higher signal intensity generated by haste sequence. However, if we look at the edges, we can notice that the edges between different tissues are actually clearer in the SSFP, while they are very blurry in the haste result. So in these slides, we can observe more closely in these 2 videos under 0.55 Tesla. We can tell that not only for fetal tissue, but also for maternal tissues, that SSFP has a clear result, despite the noisy background. But as for the cerebral region and the cardiac region, I think haste has a clearer images of that. Okay, let's talk about the challenge I faced during this project. First of all, the T1 tissue data from botany is not enough. It only covered like 1/3 of all the tissues kind I had. If provided more, I think it would create a better result. Moreover, there is not much research data on fetal imaging. I would like to compare the SNR for my result to others, but I'm lack of the data and then the resources. I realized that more research should be done for fetal imaging, and I also noticed that the trade-off I mentioned before happened for my project. For haste, it actually largely reduced the scan time, which because it only acquired half of the case-based data, and then this would make it easier for mothers with safety concern, or even claustrophobic. However, the SSFP results are apparently more useful for diagnostic purpose. It is clearer. If given more time and resources, I think I can improve the result for haste because I only used one combination of TR and TE for haste. And here is my reference page. Thank you all very much for your patience.